into my work here at Penn, where we develop miniaturized medical diagnostics. And just because I'm sitting here with a spotlight on this beautiful red carpet, you might think I did all this work myself. I did not. This work is done by my wonderful graduate students here at Penn, and this is one thing people don't realize, is cutting-edge work is often done by 22-year-olds. So these sort of young kids are the ones who are actually doing all of this work, which I'm going to tell you about today. And so the main goal of my research is to take medical diagnostics, which here at Penn, when you think about medical diagnostics, we think about big facilities with really expensive equipment that works really, really well, but it's expensive, and we don't have it in most parts of the world. And what I want to do is I'm going to take that medical diagnostics and shrink it into something the size of an iWatch, which sounds absolutely wonderful, right? You can take medical diagnostics, have it cost less than $100, be portable, and provide immediate results directly in the clinic. If this sounds like science fiction to you, it is science fiction. This is, you might recognize the tricorder from Star Trek. And I get paid for a living to make tricorders, which is like a pretty cool way to make a living. And so how is this possible? So the basis of our technology is microelectronics. So microelectronics is our ability to make extremely complicated electronics that are extremely small and extremely cheap is what has fueled our modern economy. If you think about the laptops we use at coffee shops, if you think about Amazon, where we can sort of order anything in the world we want and have it in our front door 24 hours later, if we think about the phones in our pockets, if we think about the electric cars we're all going to be driving in a few years, none of this is possible without the ability to make really complicated electronics that we can now hold in our hand. The microelectronics is what makes this possible. And what my lab is trying to do is take microelectronics and combine it with two other technologies so it can be applied to medical diagnostics. And the two other technologies are microfluidics, which just means small fluidics, which is basically plumbing. So we're going to build really small plumbing directly on top of computer chips and try to use the computer chips to measure things like cells, biological systems. And we're also going to use nanoparticles. And nanoparticles has been in the news a lot. I'm sure you've heard that word. All it means is small particle, really, 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 really small particle. So we're going to make really small particles, in this case really small magnets, which we can specifically stick to cells to make them magnetic, so we can measure them with our chips. And this is one of our chips, so it's about the size of a quarter. It's really, really small, but it does a beautiful thing. It can take blood from a patient and tell that patient whether they have cancer or not. So this is what microelectronics can do. It can make really, really small chips that do powerful, powerful things. So why in the world should you care? What is this really about? So this is a picture I like to show in my lectures. I always ask, does anyone recognize this? But this is Lagos, Nigeria. Lagos, Nigeria has 12 million people. Nigeria has 150 million people. That's like half of America. That's a huge country. And if you go back only 15 years or so, there was one phone in Nigeria for every 150 people. So if you had a telephone, you would have to share with 150 of your best friends. And that's a huge problem. So how do you solve that problem? Do you have to sort of wire up everyone's homes? You have to work with governments? You have to deal with regulation? It's an infrastructure problem. It's a really huge problem. But yet, by 2014, there are now more phones than people. The problem is completely solved. There's now way more phones than people. There's no more problem about telephones in Nigeria. And why is this possible? It's possible because of this Nokia cell phone. Right? We can build this Nokia cell phone for about a few bucks. Right? It costs about $3 to make this phone, and it costs no infrastructure. We don't have to wire people's homes. We can hand out these phones by the millions, and now everyone has phones. And so this is this is what inspires us. We say, well, if we can do this for phones, why can't we do it for medical diagnostics? And why is it important to bring medical diagnostics to the rest of the world? Well, the reason is the rest of the world, a lot of the world, has terrible, terrible, terrible medical diagnostics. So here in America, for every 10,000 people, there's 24.2 doctors, which is pretty good. It's not nearly as good as Germany, which has 36.9. But if you were to go to Ghana, there's only 0.9 doctors for every 10,000 people. So we're dealing with 25 times less physicians for every patient. And this type of lack of access has huge, 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 huge repercussions. So if you live here in America, your life expectancy is about 80 years, which is pretty good. If you were to live in sub-Saharan Africa, your life expectancy is 47.1 years. This is abysmal, right? And if you actually look back to 1990, it was 49.1 years. It's gone down. It's gone down mainly because of HIV/AIDS. And this is a huge, 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 huge problem. These people do not have access to healthcare. They're dying from diseases that we don't die from anymore, like tuberculosis. And the main reason is they don't have access to healthcare. And so what we want to do is we want to bring diagnostics to the people. This is really sort of the sort of motivation. It sounds cheesy, but that's sort of what we do. And if you can make a handheld diagnostic that costs as little as a cell phone and works like a cell phone, you can bring these expensive medical facilities directly to the clinic. You can also, there's lots of other interesting applications. You can bring it directly to the environment. So if you want to do environmental sensing, Like say you have this water reservoir in England, you don't have to drive the sample back to London to do your measurement. You can sort of throw a bunch of sensors in there and check on your laptop to see if there's any contamination. And the one that I'm most passionate about is underserved communities. If we can make medical diagnostics cheap, we can bring it to places that currently don't have access to this technology. So what do I actually do? So that's like a very big picture. And here at Penn, what does our lab actually do? Well, we work on very specific problems. We say, can we build these chips to solve medical problems that matter to real people? And the two we spend most of our time doing is one, trying to build a blood test for cancer. If you have cancer, how do you know you have cancer? If you can take a blood test and find something there that'll tell you, you might be able to catch it earlier and treat the cancer more effectively. The second one is building a diagnostic for tuberculosis that works as well as what we have here at Penn, but can go anywhere in the world. So let me tell you about how this works. So I'm trained as an electrical engineer and as a physicist, so what the heck do I know about cancer, right? And the answer is like, not as much as I should. Turns out engineers can build diagnostics and things that really matter to healthcare. But the way you have to do it is you have to work with physicians. So here at Penn, our engineering school is very close to our health center. And we always make that walk back and forth. And that walk back and forth is the key aspect of this technology. It's electrical engineers and physicists talking to physicians. And that conversation is where this technology comes from. And so right now, if you wonder if you have cancer or not, the main way you find out if you have cancer is through a biopsy. You have to open a person up, stick a needle in, extract some tissue, and look at the tissue and see, are there any of these molecular markers that tell you that you have cancer or not? This obviously is not something you can have done very often. It's very painful, and it's expensive. What we would love to do is take a blood test from a patient and find something in that blood that can tell us the same thing that the biopsy could tell us. Well, it turns out cancer does us a favor. The cancer cells occasionally shed off into the bloodstream and circulate. This is actually how cancer spreads. This is how metastasis works, so it's not like a good thing, but for a diagnostic, it's an opportunity. We can find these cancer cells in the blood and use those to diagnose cancer. Now here's the challenge. So if you take blood, this is a tube of blood you get from a patient, and it's 7.5 mils of blood. This is sort of typically what we get. You have billions upon billions upon billions of cells, and only about 0 to 200 of these tumor cells. So you're looking for a needle in the haystack. So how do you find a needle in the haystack? Well, we said, why don't we build a hard drive? So if we think about the hard drives in our computers, they can read megabit files, so millions of bits per second, right? And I said, why don't we take a hard drive and flow the cells over the hard drive? In the same way we can read millions of bits per second, we can read millions of cells per second and screen through these enormous numbers of cells and find these cancer cells. And you know what? It worked. So we're able to take blood from cancer patients, and we took blood from them, and using just our blood test, we could identify all the patients, 100% of them, whereas any other conventional technology using blood could only catch about 15%. So this is an example of how it works. And so you might be asking, well, wonderful, why is this guy not super rich and living on an island and still working? Well, the answer is it's far too slow. So even though this chip can go quite fast, can read thousands and thousands of cells per second, it's still too slow to be meaningful. Because when you take blood, you have billions upon billions of cells. And so we're still about a factor of 10 to 100 too slow. So how do we go faster? Well, we go faster by, again, pulling from the same trick that we use in microelectronics. So all of us have cell phones in our pockets. All those cell phones have cameras. All those cameras have megapixel cameras, right? That means millions of pixels, meaning that you can have millions on millions of sensors all measuring light at a given time. So what we're doing now in our chip is rather than building a single hard drive, we're building chips that have millions of hard drives. And rather than measuring cells in one stream, we're measuring cells in millions of streams. And so now we can go potentially 1,000,000 times faster. And this is one of the main things my lab is working on here at Penn. How do you take these ultra-sensitive tests and run them fast enough that they're actually meaningful to clinicians? And so beyond cancer cells, we can also go much smaller. So beyond cancer cells, we're also looking at bacteria, which is about 10 times smaller than a cancer cell. We're looking at HIV virus, which is another 10 times smaller than that. And we're looking at exosomes, which are these little tiny particles which are shed from tumor cells that are even smaller than that. And so we can build technology that scales all the way down to the biological targets that are actually meaningful. So there's another kind of cancer for which our cancer cell blood test won't work, and that is brain cancer. So in particular, we're interested in pediatric glioblastoma, so childhood brain cancer. It's a terrible, terrible disease. 5-year survival rate's about 20%. Affects mainly children 9 to 10 years old at diagnosis, and at two-thirds of the time at diagnosis, the cancer's already spread. So we're catching it really, really late. Now the problem is, in the brain, things don't get into and out of the brain very easily, so there's no cancer cells. But it turns out there are these things called exosomes, these tiny little particles the cancer cells shed, which do end up in the bloodstream. And so the question is, how the heck can you measure these things that are so small? And so what we do is we use a new kind of technology called digital microfluidics, where we take a sample, we break it up into millions upon millions upon millions of pieces, and run chemical reactions in each individual piece. Now, this is something that's working in people's labs right now, but it's too expensive because you have to shine a laser at each droplet and count that droplet. So how do we do it? Well, one of my talented graduate students figured out that you could basically give each droplet a cell phone. Not exactly, but by analogy, you give each droplet a cell phone, and rather than having to measure each one individually, it sort of calls you and tells you that, hey, I found something. And so by harnessing the same kinds of technologies and tricks that work in microelectronics, we can build things that are extremely complicated into extremely powerful things, but cost hardly anything. So it's a very important part of this work is translating it to the clinic. So we often work with physicians. This is something I really want to sort of press to you people, is that this work really requires conversation. That's something we do a lot here at Penn. And also it requires education, because I'm really inspired by my own educational experience, training as an electrical engineer and thinking that I didn't really want to do any of the applications that were presented to me. And so this is a class we have here at Penn where we take students to Ghana and show them applications that they can actually, things they can build using these types of technology. This is something I'm very passionate about. So thank you very much, and that's the end of my talk.